Welcome back. Now we'll look at paper 31 from May-June 2024. Now originally I did plan to upload all of the AS papers, right, then I'd move on to A2. However, someone did request that I upload some paper 3 and 4s. So what I'm now going to do, I'm going to upload all of 24 for both AS and A2. Then I'll move on to 23 again, upload both AS and A2. And of course, then 2022, 2021. And as always, of course, the mark scheme is available already, so I do recommend checking that. And if the video is too slow, then I'd recommend watching at 1.25 or 1.5 times the speed. Okay, question 1, it says real numbers are stored in a computer system using floating point representation with 10 bits for the mantissa, 6 bits for the exponent, and 2's complement form for both the mantissa and exponent. Calculate the denary value of the given normalised floating point number. Right, and we need to show our working. So first then, let's say here we can draw the decimal point. Then we want to look at the exponent. Because of course, this will tell us how many places to move the decimal point by. Or I suppose, let's not call it decimal point. We can call it a binary point. So what we want to think, if we just kind of approximately think about this, of course, this is going to be 0.5. Then we've got that was going to be I suppose this one's going to be 1/4. This is 1/8. Right, that's 1/16. So I don't know, approximately this is, let's say, 0.6, right, something. And then we say it's going to be multiplied by, here if we look at the exponent, that's going to be 2, and then to the power of 9. Now 2 to the power of 9, right, I think that's going to be 512. Of course, 0.6. So if we think 0.6 times 512, approximately, I don't know, maybe 300, right, approximately. So, let's just keep that in mind, when we're trying to actually, work out a real answer. Now, of course, in the exam, you don't have to do this. But, I know some people get confused. They think, do we move the binary point to the right? Or, do we move the binary point to the left? But if we think, again, this is approximately, let's say 0.6. 2 to the 9 is, 512. Right, therefore, we should get an answer of approximately 300. Of course, if you get an answer of 0.0005 or something, then of course you've moved the binary point in the wrong direction. Anyway, so let's just do this then. We want to move the binary point 9. So just 1, hang on, 2, right, 3, 4, 5, 6, right, 7, 8, and 9. Alright, so here then the binary point is at the end. So what I'm going to do, I'm just, since we do need to show our working, I'm probably just going to write down the positional values. So let's go 1, 2, right, 4, right, 8, 16, 32, right, 64, right, 1 to 8, right, then it's going to be 2, 5, 6, and I think, finally we should have 512, and if we just write these values, so what we've got, 0, 0, 1, 1, right, 4 1s, alright, then, 2 zeros, and, hang on, right, that should be a 1, right, then 0 here. So what we can do then, let's just sum this up. So 256 plus 32, that's going to be 288, right, then 294, right, 304, right, 312, 316. Right, so 316, and I suppose, in the exam, if you want, you could write 316. Of course, you could also do, 256, right, 32, 16, right, 8, and 4, and of course you could sum it like this. But I think, they should just accept, right, this working. Right, then we want to calculate the normalised floating point representation of minus 102.75. So if we have a negative value, and of course, even if it's positive, first we want to convert it to fixed point. Right, but what I was going to say, that for negative, we actually want to go to minus 103, right, not minus 102. Because if we think about this, it's going to be minus 103, right, plus 0.25, and that's going to equal our minus 102.75. Some people make the mistake of trying to calculate minus 102, but of course, in this case, right, then there's no way to actually minus this 0.75. That's why it should be right, minus 103. Right, so what I'm going to do then, I'm just going to write out minus 103, so that's going to be, if we just write this again, right, minus 128, let's go 64, right, 32, 16, Okay, again, yeah, all right, 16, 8, right, 4, 2, 1. Right, of course, well then here it's going to be 0.5, and let's go 0.25. Now for minus 103, I suppose we want what? We want a negative 128. Then we just want to make 25. So to make 25, that's going to be a 16 and 8. Right, that's going to get 24. Right, then we're just going to have a 1. And yeah, I'm just going to write the sort of decimal point, or well, the yeah, I guess the binary point. Right, then we want to get, well, plus 0.25, because again, minus 103 plus 0.25. All right, yeah, that will get us the right, minus 102.75. So right, if we just want plus 0.25, of course it's going to be this. Now, right, since this has to be normalized, well, we want to think, right, how can we move the binary point up? And of course, remember that if it's negative, well, it should start at 1.0. Now, if it's positive, it should start at 0.1. So we just want to think, right, this is going to be 1, right, 2, yeah, 3, 4. Okay, right, so that should be 7. So let's just write this then. This is our mantissa. And of course, I mean, well, we don't need to write the dot, but I'm just going to do it just to visualize. Right, then what, 1, 1, 0, 0. Okay, yeah, so that sort of fits nicely. Right, then the exponent is just going to be 7. So of course 7, well, just what, a 4, a 2 and a 1. 2 says the TCP IP protocol suite has 4 layers. Right, that's transport, application, link and internet. And we want to complete the diagram to show the correct order of the 4 layers. Right, so the top one then is going to be application. An application, if we think of some of the protocols, for example, let's say HTTPS, right, SMTP, I think, well, the send mail transfer protocol, right, POP3, post office protocol, yeah, IMAP, maybe instant message transfer protocol, yeah, or maybe internet message, I'm not sure. Right, also BitTorrent, you know, FTP, right, file transfer protocol, yeah, SSH, right, secure shell, yeah, so I think many for those. Right, then if we think, well, under the application, that's going to be the transport layer. And then the transport layer, well, that's going to include TCP or UDP. Right, then there's going to be the internet, yeah, also called the network layer. And well, I mean, internet, that's just going to be IP. I think, you know, maybe 20 years ago, you know, there was actually more. But yeah, these days, I mean, it's mostly just IP. Maybe if you have some sort of, yeah, like private network, which is using your own hardware or something, you know, you might have something different. But yeah, for like 99.99999% of people, yeah, this is just going to be IP. Right, and then, well, finally then that's going to be link, and yeah, this is really just Ethernet. Right, that's going to be the main one. Right, so we want to describe the function of the transport layer. So I guess, I mean, well, again, we said, well, there's 2 protocols. One is TCP, one is UDP. And we can say, well, obviously TCP is going to be more reliable because, well, this will ensure a couple of things. One, well, all the data is going to arrive, and 2, I mean, the data should also be in the correct order. Whereas if we think UDP, I mean, this is just going to send the data, you know, in like a continuous stream, and I mean, hopefully that data arrives. But yeah, maybe some of it doesn't, right? Maybe some of it arrives in the wrong order, because of course, you know, they've gone like different routers. So yeah, maybe one goes, you know, sort of this route, right? These routers. But yeah, another one might go to, I don't know, you know, these routers here. And yeah, of course, well, then they can arrive out of order, right? The packets. But I think, well, okay, let's say the main purpose of it is actually going to be to do with the port numbers, because I mean, what we can think is that, well, when you send data to a computer, you know, the computer actually has many different applications running. For example, maybe you have a web browser, you have a game, maybe you have some like instant messaging software, I don't know, you know, like WhatsApp, right? You might have like your email client open. So of course, I mean, well, when you know, when this data arrives at the network interface card, right, or wireless network interface card, of course, well, like, yeah, I guess, well, obviously that's going to be passed on to the operating system. But then the operating system has to think, well, like, I mean, what data, or okay. So let's say, what application, right, are these packets actually for? Yeah, are they for, you know, the web browser? Are they for the game? Right, yeah, what are they for? So that's where the port number is going to be used. And to be honest, I mean, you can, for example, just go in Task Manager if you're on Windows, and yeah, I mean, you can see the port number. Likewise, of course, on well, sort of, yeah, Mac, Linux, right, I'm sure there's tools. Of course, you can also do this right via the command line. Yeah, see what processes are listening at what particular port. But anyway, I mean, let's try and add this. So what it's going to say, let's say add the port number. Yeah, let's say what, 2 packets. And I suppose technically we're actually in the transport layer, they're going to be called segments. So let's just write that, yeah, segments. Of course, the internet layer, they're called packets. And then, yeah, the link there, they're going to be called frames. Now, to be honest, I think like most people really just call them packets for all the layers. Yeah, it kind of just gets like sort of mixed into one. Right? Otherwise, it's quite difficult to remember the 3 different names. So yeah, I'm just going to say packets, and then in brackets, I'm going to put segments. Right. So yeah, okay. Let's say, yeah, maybe adds the port number to packets. Let's say to ensure. Right, let's say that the packets are delivered to the correct application. Okay, yeah, right, delivered. Yeah, let's say to the correct application. Yeah, let's say the correct application on the receiving device. Right, and then I think, yeah, maybe we can also talk, for example, about TCP, so about, let's say, the reliability, and also, yeah, the reordering of packets. So let's say, I don't know, maybe in TCP, or yeah, if, okay, let's say if, right, if using TCP, let's say a packet number or a sequence number will be added. Right, yeah, a sequence number will be added. And we can say let's say this, yeah, this maybe ensures, or I mean, yeah, okay, I mean, let's say this ensures, or yeah, this allows checks to make sure that all the packets have arrived. So this ensures, right, all the packets, yeah, right, all the packets have arrived. Yeah, and that they can be rearranged into the correct order. Okay, yeah, that they can be rearranged. Okay, right, rearranged into the correct order, right, by the receiving device. Yeah, okay, so I think that's fine. Now, I was a little bit unsure about this, where I said, right, this ensures all the packets have arrived, because obviously, just adding the sequence number doesn't actually ensure they all arrive. But of course, it's going to be the checks following that, where, I mean, yeah, well, of course, obviously, if the device doesn't receive, some of the packets, right, then they're going to be retransmitted, yeah, based on the acknowledgement number, right, the sequence number. Right, anyway, next we want to outline one protocol that is associated with the application layer. So I think probably the obvious one, I mean, of course, we've mentioned a few like email protocols and others, but let's just go with HTTPS. We can say this is used to request web pages. Yeah, okay, let's say that. Right, yeah, this, yeah, okay, all right, yeah, this is used, right, to request web pages from a server. Yeah, or let's say from a server. And let's just say securely. And we can say I don't know, maybe like encrypted communication. And I mean, I think then we can also say what the server will respond, right, with those resources. Yeah, okay, right, let's say the server will, I guess will then respond. And I suppose, I mean, not always is it going to be the actual resource they're requesting, because, maybe they have an error code, like a 404, like a sort of file not found. Of course, it could be a 500, like an internal server error. I think 503, that's going to be permission denied. Yeah, let's say they're not logged in, right, or they're trying to access some, like, admin section or something like that. So let's say, yeah, we'll then respond, let's say with, let's say, right, a file, right, yeah, / maybe error code. Yeah, I think this you just say, respond with a response. But yeah, I mean, this is probably a little bit more specific. Now it says, explain what is meant by non-composite and composite data types. So I think if we say non-composite, really, you can just think of primitives. just what obviously, yeah, integer, real, right, string, boolean, char, yeah, I guess even date. So you say, well, these will just be, let's say, kind of simple values, right? Just, one individual value. Whereas if we say composite, well, these will actually be, for example, like multiple values. Now, let's say you have a record. Of course, you can have a record, let's say it's a person. Right now, this might have a name, which is a string. It might have an age, which is an integer. Yeah, I mean, probably a date of birth would be better, right? Of course, that's going to be a date. Yeah, maybe there could be a gender, right, which is, char. Of course, there can be, I don't know, something that's, true or false. Yeah, maybe like whether they passed the exam, right, true or false. So, yeah, let's just try and say that. Then we can say non-composite. Yeah, let's say what non-composite data types contain single values. Let's say what, e.g., well, primitives, right, like integers, yeah, reals, etc. Yeah, all right, let's go what, integers. Yeah, I don't know, maybe let's say booleans. Although I think actually Boolean should be big B, right? Because it's the name, yeah, George Bull. Right, so integers, Booleans, right, etc. Yeah, and then well, let's go what in contrast. I was trying to think if there's anything else we want to say for non-composite. Yeah, I don't really think there is. Right, in contrast, let's go non-composite. Right, non-composite data types. And I suppose here we can say what they can be user defined or built in. Yeah, okay, right, can be user defined. So of course, well, this would be a record. Right, or built in. Now, of course, I mean, this is going to depend on the programming language. But let's say, for example, Java. I mean, Java has a lot. For example, where you've got an array list, you've got a hash map. And well, so I mean, a hash map is just a sort of, yeah, I guess a hash map is a dictionary. Yeah, well, of course you've got sort of, linked list, priority queues, right? Yeah, there's going to be loads. Right, so non-composite data types, right, can be user defined. Yeah, or well, let's say right, or built into the language. Then we can say what records are examples. Okay, well, let's say yeah, records are non-composite. Right, since they contain multiple values, or yeah, since they can contain multiple values. Yeah, so I don't know, maybe let's say e.g. a person record. Yeah, let's just give the example, a person record. Right, that has, sort of string, integer, Boolean attributes. Yeah, let's say maybe attributes, right, of different types. Yeah, okay. And I mean, I suppose here, I mean, it doesn't really have to be different types. If you had a person with like 2 strings, right, maybe your first name and last name, that would also be a composite. But I mean, really, it's about having, yeah, sort of multiple, let's say multiple values. Right, yeah, attributes. Yeah, so I think I'm just going to dig that, or maybe like multiple attributes. And yeah, let's say what e.g. Okay, let's say yeah, e.g. name. We'll say in brackets, right, string. And then we can say, I don't know, maybe like date of birth. Right, and of course, well, that can be a date. And then, yeah, let's go, etc. Right, then we want to write pseudocode statements to declare the record type football club to hold data about football clubs in a league. Right, so, I mean, I think, well, let's just do this as we're kind of writing, or yeah, as we're reading. Right, so let's go, hang on, right, okay, yeah, T, right, type. Right, so this is then going to be football club. Yeah, okay, right, these are small letters. Right, well, then, I mean, inside here, then we just want the declare statements. Same as how we would, well, yeah, same as how we would declare any variables. Right, so let's just go name, and of course, well, that's going to be string. Right, I mean, I'm not going to write the declares, although, of course, yeah, in the exam, you would want to write them. Right, so I mean, I guess here what maybe like date joined. Right, and of course, well, that's going to be date. Right, the next one, I mean, what main telephone number? I mean, let's say like tel, right, telephone number. Right, now the telephone number, I mean, some people might think integer, but I think probably a telephone number should be a string. And the reason for that is, of course, well, sometimes you have, let's say, the country code, which, yeah, obviously that's going to be some numbers right inside brackets. Maybe you're going to have, I don't know, like 000, you know, sort of 1, 2, 3, you know, 4, 5, 6. So, of course, you're going to have these hyphens as well. So, yeah, I think, well, let's make this a string. Right, I guess what, manager name. And of course, well, manager name, right, that's also going to be a string. Right, then the number of members, let's maybe call it like member count. Right, and of course, well, that's going to be an integer, right, since we can only have a whole number of members. Right, then the current position in the league, well, again, that's also going to be an integer. So let's call it maybe league position. Right, and again, of course, yeah, that's going to be an integer. Right, and then, well, since we have type, of course, let's make sure just to have the end type. Yeah, I think, well, I mean, everything in pseudocode, you know, if you have an opening part, right, you're also going to need the closing, you know, like if, end if, right, for, next, yeah, repeat until, right, there's always a corresponding end. Number 4 says, describe the sequential method of file access. So what we're going to have then, we're going to have, let's say each record will have a key. And what's going to happen is that, well, we're going to start at the beginning of the file. Right? Of course, we're going to look at the first record. If the key is not equal to the file that we're trying to find, right, then, of course, well, we're going to go to the next record. Again, we're going to, you know, compare those keys, obviously, yeah, etc., right, until we find the file. Okay, hang on, right, sorry, until we find the record, right, or until we've, you know, reached the end of the file. So let's just say that, let's say, yeah, well, okay, let's say records, yeah, records will be accessed one after the other, right, starting from the beginning of the file. Yeah, let's say, right, one after another. Right, from the start of the file. Right, and then what we can say, yeah, well, okay, let's say, right, this will continue. Right, until, and let's say what, until we have found a record with the correct, let's say what, ID or primary key. Yeah, okay, right, so until we have found a record. Yeah, and okay, I mean, okay, so let's say the thing with this is, unlike a database where, you know, let's say every primary key should be unique. Now, in this case, I mean, they actually don't have to be unique in a file. And the reason for that, I mean, let's say we have something like, I don't know, maybe a purchase. Now, okay, I mean, let's say the key is just, you know, this sort of, yeah, let's say the sort of, you know, customer. So it's their customer ID. Now, of course, you know, you can have, let's say, like one customer, or let's say customer 4. And, you know, of course, well, they have one purchase here. Or then customer 4, of course, well, they have another purchase here. So, of course, yeah, we see, right, we have the key duplicated, right, multiple times. Anyway, right, so, yeah, this will continue until we have a record. Or, yeah, maybe, let's say we find a record. Yeah, what, with the key that we are searching for. Yeah, that we are searching for. Right, and then, yeah, or we have reached the end of the file. Now, I know sometimes, right, end of, yeah, the file. Now, I know sometimes they do also say that you can also stop, right, once the current record key is bigger. Because, for example, I mean, let's just say we have the records, maybe 1, right, then let's say a 3, let's say a 4, right, let's say, I don't know, 6. Now, let's imagine we're searching for record 5. Of course, well, first we check 1, right, yes, obviously, well, this is false. Right, of course, well, then we go to the next record 3, right, again, that's false. Then we check 4, right, well that's false. And actually let's say there's, for example, 8, right, 9, yeah, 10. Right, okay, well now we, yeah, of course, well now we get to 6. But what we see is, well, of course, 6 is bigger than 5. And since we've actually not found our position, or yeah, I guess, well, we've not found our record, right, then of course we know that the, well, of course, yeah, we just know that that record is, not stored in the file. Now, yeah, like I would say you could probably say this, although if, for example, you have, let's say, string keys, then yeah, this is a bit more complex with string keys. I think sometimes they're actually not necessarily going to be ordered. But anyway, right, if we go to the next one, it says explain how the sequential method of file access is applied to files with serial organization and to files with sequential organization. Okay, I mean, so isn't this what we just said? Okay, so I suppose, I mean, the difference then is, what if it's sequential, well, if the file is stored in a sequential order, this is going to be where it's actually ordered, well, yeah, of course, it's just ordered, based on some key. Whereas if it's serial, well, it's just going to be ordered in chronological order, where we say, obviously, what the, let's say, the sort of new element, or, well, okay, right, the new record is just going to be appended to the end of the file. Yeah, I mean, so let's say that maybe. Although here they are talking about access, right, not really storing them. So let's say, yeah, with serial organization. Right, yeah, with serial organization. Let's say what the records are stored in chronological order. And of course, well, chronological, I mean, this just means time order, right? So let's see what the oldest one is at the start of the file, right? The newest one is at the end of the file. And let's explain that, right? So yeah, hence when we are doing a, yeah, okay, well, like hence, right, sequential access will kind of, go through the records, obviously, yeah, starting from the oldest, right? And then we'll ultimately go into the newest. Yeah, let's try and say that, right? Hence the sequential, yeah, let's see what the sequential access method. Right, will, I mean, what sort of like, yeah, loop through the records. Yeah, I mean, I think we can probably say that, right, loop through the records. Or you could say, yeah, check the records. Right, well, of course, yeah, just in time order. So what we can say, what, from oldest to newest. And then here, yeah, okay. And I suppose what here we can say, what, until it finds a match. Yeah, okay. Okay, well, all right, let's see, yeah, until it finds the record it's searching for. And I don't know, I mean, like, I think this one seems similar to what we've just written. So let's see what with, yeah, with sequential organization. Right, we can say what the records will be ordered based on a key. Yeah, let's say, right, will be ordered. Yeah, okay, right, ordered, right, based on a key. What, like, hence, yeah, what, so, well, again, I mean, let's say what we search until we find, the correct key, right, or we stop if we exceed the value of that key. Okay, right, yeah, so search, right, until we find that key. Okay, well, let's say find the record with that key. Right, yeah, okay, let's say, right, or we, yeah, I guess what, or we stop, or yeah, we sort of fail. Right, if we, yeah, let's say if we have reached a record. Okay, yeah, reached a record. And we'll say what, with a key exceeding the value of the key that we're searching for. yeah, right, so with a key, yeah, exceeding, right, or greater than, right, the key we are searching for. Yeah, I mean, I think that's enough. Although, to be honest, I mean, well, yeah, for me, these questions seem pretty similar. 5, we need to write this reverse Polish notation, or RPM, in infix form. So the way we convert this then, well, we're just going to use a stack. And yeah, here's a bit annoying. They actually don't give us much room to do this. Yeah, I'm going to make this quite big because, well, we're probably going to get quite long expressions. So what we do, while working from left to right, we just push 5 onto the stack. Right, then we push 2 onto the stack. So, I mean, okay, let's say, right, if it's a number, right, or of course this can also be an identifier, like, you know, A, B, C. But if it's a number, or, you know, okay, well, let's say number, right, variable, right, then we push it onto the stack. If we then see an operator, well, then, I mean, if we're evaluating it, right, finding the answer, of course we would do that sort of, you know, calculation. If we're just actually, yeah, if we're just actually kind of, you know, converting the expression, well, then we're just going to rewrite it in that format. So here then that's going to become, what, 5 plus 2, and here we should put this in brackets. Right, then we've got 9, so we're going to push that onto the stack. Right, then we get 3, so push that onto the stack. Right, then what we do, the same as we just did, and I think, yeah, I didn't really explain it that well. So since here, right, we obviously we see an operator, we're going to pop the top 2 elements off the stack. So, I mean, 3 goes here, 9 goes here, and then right in the middle, yeah, we put the minus. And make sure to have it the right way, because of course if you did 3 minus 9, that's going to be wrong. So what you say is, okay, let's say the sort of first one we pop off goes on the right. Yeah, of course, right, the next one goes on the left. Right, so if we just write that then, right, 9 minus 3. Right, let's write that here, yeah, 9 minus 3, again, that goes in brackets. Right, then we get a divide. So, and yeah, I mean, this is where we're kind of using too much space. So I suppose for a divide, what if we pop that off the stack, right, then we've got a divide, and of course, what in this case, yeah, of course, what in this case, right, the 5 plus 2 was the bottom element, the 9, yeah, the 9 minus 3 was the top element. So of course, well, we're just popping those from the stack. Again, let's put that in brackets, and yeah, I'm going to just sort of draw the stack back in, right, make it a bit bigger. Right, then what do we get? So we get a 3, right, let's push that onto the stack. Right, then we get the multiply. So again, what we're going to do, well, of course, we yeah, pop that from the stack, and of course, yeah, I mean, basically we do this, right, where of course, well, this one is going to be the top element, right, this one is the bottom element. So if we just want to write that, well, let's just do more brackets, and of course, yeah, this is then going to be our final answer. Right, now we want to write this infix expression in RPN, so yeah, just going the other way. Right, so doing that, then what we're going to do is called, what, the Shunting-Yard algorithm. Like, this one is maybe a little bit more complex. If people want to see a full video, yeah, just search, well, Shunting-Yard. You know, of course, you can also just type in, you know, what, infix to RPM, right, or yeah, maybe like infix to postfix. Right, there's obviously going to be many videos, right, showing how to do this. There's also actually a lot of websites that will kind of demonstrate this, where, for example, let's say you just think of some random expression. You can, of course, then type this into the website, and well, the website will give you the correct answer. So if you just want to make your own questions and practice, yeah, I would recommend finding websites that, you know, perform these conversions for you. And yeah, I mean, okay, well, there's websites that do all of this, right? Infix to RPN, you know, well, sort of RPN postfix to infix. Yeah, other ones that do the evaluation, right? Just everything. Anyway, so what we want to see then, well, if we see a bracket, and well, okay, here then we're going to have a stack, right? And then we're also going to have a queue. So if we see, let's say, what, a bracket or an operator, then we're going to push it onto the stack. So here we see a bracket, right, okay, then we see another bracket, so let's also push that onto the stack. Right, then we see, okay, well, let's say a number or a variable. So any number or variable, well, we just enqueue that, right, add it to the queue. Right, then we see a plus. Now, what we check is, well, if there's an operator below it with a lower precedence, right, then we actually pop that operator off the stack. Yeah, and continue popping them off the stack, right, and just adding them to the queue. However, if we think actually brackets have a higher precedence, because, well, okay, I mean, let's just sort of recap. Of course, well, plus and minus, right, okay, and plus and minus, they have the lowest precedence. Well, then we have yeah, divide and multiply, right, they have high precedence. I suppose if you want, you know, you can also talk, let's say, like the power or exponentiation. and then finally you're going to have the brackets. So of course, yeah, brackets has the highest precedence out of all of these. Therefore, what that means then is, well, the plus is going to get pushed on. Right, then we see a 3, so let's just write that, or yeah, add it to the queue. Right, now we see a closing bracket. So if we see a closing bracket, then what we do is, well, we pop everything from the stack and we add it to the queue. However, I mean, brackets we can ignore, right? So basically we pop all of the operators from the stack, right, until we find a corresponding opening bracket. I mean, okay, well, so just to sort of recap that again, I mean, because, you know, here, of course, we have this closing bracket, right, therefore we're going to pop this, right, then when we see the opening bracket, of course, well, we pop that as well. Okay, I mean, let's say this opening bracket we pop, but we don't actually add it to the queue. So yeah, I mean, right now what we're going to have is this, and I mean, like, hopefully people are familiar with this method already. I mean, they should have practiced. So yeah, this should just be recap. Okay, right, so then we see a minus, so yeah, let's push that to the stack. Right, so now we see another opening bracket. Right now we see a 2. Right now we see a multiply. Right now we see an 8, so yeah, let's right, in-queue this. Right, again, so now we see another bracket, so what we're going to do, we're going to pop everything from the stack, right, until we find the corresponding opening bracket. So in this case, right, that's only going to be this multiply. Right now we see, yeah, okay, alright, so well, now we see another bracket, so we're just going to do the same. So of course, well, yeah, obviously the minus we've popped from the stack. Right, then we see a divide. So yeah, okay, this divide we're going to yeah, add to the stack, or push to the stack. Right, then we see a 6, so of course just in-queue this, and then when we get to the end, well, anything in the stack, right, we just pop off. Of course, you know, starting from, well, the top going down. Now in this case, of course, there's only one, right, there's only one operator. So yeah, I think this should be our final, yeah, final expression, right, in infix. Right, now we want to evaluate this RPN expression, right, so A, B, right, minus CD, yeah, whatever. And here it's telling us the values. So in this case, well, I mean, actually this is the same as what we just did here for this first one. But like, rather than just sort of, you know, considering this as a string, basically, you know, we're just going to perform these calculations, right, like 5 plus 2, for example. So what we say then, well, right, first we get 17 because, well, that's this A, so right, push this to the stack. Right, then we get B, so that's going to be, in fact, okay, let's actually do this here in the next one. Right, B is therefore going to be 5. Right, then we get a minus, so what we said, we take, well, of course, the first element, right, minus the second element. So that's going to be, what, 17 minus 5. So yeah, this will then be 12, and of course, well, we push that back to the stack. Right, now we get a C, and C is going to be 7, so right, hang right, 12 and 7. Right, then we get a D, so let's write this 12, 7, and then what D is going to be 3. Right, then we get a plus, so again, well, 7 plus 3, right, that's going to be 10. Yeah, let's just write the 12 there as well. Right, then we get a multiply, so what, 12 times 10, right, that's going to be 120. Of course, yeah, pop both of them from the stack, right, then add the answer back to the stack. Well, yeah, push the answer back on the stack. Right, then we add this E, I think. Right, so E is then going to be 10. So right, we've got, what, 120 and 10. And yeah, then we've got, what, 120 divided by 10, so pop those from the stack. And then, yeah, just write the answer. Alright, so that should be 12. Okay, 6, we have some, right, diagram shows logic circuit. Yeah, I mean, it looks quite intimidating, but I think it's actually not too bad. Right, complete the truth table, yeah, for the given logic circuit and show you're working. Now, I'm just going to zoom out just so we can see the logic circuit, yeah, as we're writing the truth table. Okay, so let's try and do P then first. So if we look, what P is just going to be not B. So of course, well, right, if we see B is 0, right, therefore not B is going to be 1. Of course, yeah, 0, 0, right, 1, 1, 0, 0. Right, then Q, so Q is going to be, what's it, A. Right, then this one, okay, so yeah, this one is going to be B. Let's just write these. And then what, this bottom one is just going to be C. So here, what, just, yeah, A and B and C. So where A and B and C, right, is only going to be true in this case, and then of course, yeah, everything else is going to be false. Right, then the next one, R. So right, what is R? Okay, so right, this one is going to be C. Right, this one is going to be what, not B, and then yeah, this one here is going to be A. So right here, then we're looking for, well, of course, yeah, A should be 1, right, C should be 1, and then yeah, of course, well, not, yeah, not B, right, so that's going to be 0. Right, so is there anywhere we have, yeah, 1, I guess, what, 1, and then, yeah, sort of 1 and 0? Okay, sorry, yeah, 1, 1, 1. So, right, I think it's going to be, yeah, this row here. Because if we see, well, of course, yeah, P is 1, and well, P is just not B, alright, then, yeah, A and C are both 1. So I think, yeah, it's just going to be that one. Alright, and then, yeah, all the others are just going to be 0. Right, then S, so, right, S is going to be, right, yeah, okay, so, right, S is going to be A, right, and also, well, P. So, well, here we're just checking, right, where A and P are different. So here we've got what, 0, X, or 1, right, therefore that's going to be 1. Right, 0, X, or 1, that's going to be 1. Right, 0, X, or 0, that's 0. Yeah, okay, 0, right, then, well, 1, X, or 1, okay, that's the same, right, so 0. Yeah, 1, 1, right, 0. And then, well, okay, 1 and 0, and 1 and 0. Right, then we just want to OR all of these together. So what this is going to be Q, R, and S. Right, so here, well, Q, R, S. Okay, well, here we've got 1. Yeah, 0, or 1, right, that's a 1. Right, 3 zeros. And then right here there's a 1, here there's a 1, and here there's a 1. Next, we want to write the Boolean expression that corresponds to the logic circuit as a sum of products. So yeah, I think some people, you know, they kind of get confused, right, what this sum of products is. But what this just means is, well, we look at where the output is 1, so of course, well, here, and yeah, obviously these 3 as well. Right, then we just look at the 3 inputs. Well, yeah, of course, well, in this case, there's 3 inputs. So, well, obviously, yeah, we look at the inputs, right, that make this kind of the output 1. So, of course, in this case, well, input, well, yeah, 0, 0, 0. So when we say 0, well, that just means not, right? So, yeah, not A, not B, and not C. So let's just write that. So, yeah, I'm just going to do, yeah, A, B, C. Let's just not them at the end like that. So, yeah, not A and not B, right, and not C, right, that's going to equal 1. So, of course, we're saying, well, this row equals 1, right, and then or this row equals 1. So then we just, yeah, okay, so, well, then we just OR the rows together. Then if we look at the next one, well, this is not A and not B, right, and C. And notice how here, well, C is 1, right, therefore it's not C, right, it's just, you know, sort of regular C, right, normal. So yeah, that's going to be what, not A, okay, yeah, not A, right, and, yeah, not B, and then what, yeah, and C, okay, like that. Right, and then what, all the next one, so this is going to be what, A, yeah, A, not B, alright, C. Yeah, okay, right, then the next one, so that's what, A, B, and not C. And then, right, finally, well, that's just going to be A, B, C, right, all ones. And I mean, like, okay, I mean, so this one, if you do want to check, of course, it's quite easy. So you see, well, this one, right, not A, not B, not C. Well, of course, right, that should be 0, 0, 0, which is fine. The next one, well, this should be 0, this should be 0, this should be 1. We see here, yeah, 0, 0, 1, that's fine. Of course, what's 0, 1, okay, hang on, right, yeah, sorry, 1, 0, 0. Okay, sorry, yeah, 1, 0, 1. Which, yeah, of course, we see this row, and of course, likewise, you can do it for the next two as well. Yeah, I think that's why these are quite easy, because, again, it's quite easy to check your answer. Right, now we want to complete the Karnaugh map, right, K-map, for the Boolean expression. Okay, so what we look here then is we say, well, if it's not A, right, this means 0. Of course, well, yeah, 0, 0, 0 in this case. So here then we're just looking for 0, 0, 0, which is going to be this. So here, well, okay, right, so here we write 1, because we're saying, well, let's just go X. Right, of course, we're saying, well, X is going to be true, right, if, you know, obviously, yeah, this is true, right, or this, right, or this, yeah, or this, this. Right, so the next one, well, this is just going to be what, 0, 0, 1. So here again, we've got the 0, yeah, then, well, 0, 0, 1 is going to be this. Because what we say, of course, well, right, this first one is B, right, this next one is C. Right, then if we look at the next one, so, well, now we've got an A, so we're looking for a 1, and then, well, not B, not C. That's going to be, well, okay, 1, 0, 0. So, yeah, 1, and then, well, 0, 0 is these, right, that's going to be a 1. Then this one, right, that's going to be, what, 1, and then that's 0, 1. So, yeah, if you see, right, 1, 0, 1, okay, that's going to be this. Right, then if we look at the next one, so, what, that's going to be 1, yeah, 1, 1, 0. Right, so I guess, yeah, so here is the first one, and then, yeah, 1, 0. So, right, that's that, and then, well, A, B, C, right, so just 1, 1, 1. Right, 1, 1, 1 is going to be this. Right, then, of course, we can fill in these two with zeros. Right, then draw loops around the appropriate groups in the K-map to produce an optimal sum of products. So when it says optimal, of course, well, this means, simplified. Now, there's a couple of rules, remember, for doing this. One, it has to be a power of 2. So let's say, 2 to the n. So, for example, of course, well, we can draw a block around a group of 4. But we couldn't, for example, make a group of 3 because, well, 3 is not a power of 2. Likewise, it can only be, let's say, let's say horizontal or vertical. Right, we can't have any, diagonal blocks like this. Something else to remember, okay, we can have wraparound. So I think we'll actually, I suppose in this case we don't actually have to. But let's say we have something like, I don't know, maybe 1, 0, 0, 1. Now in this case, what we would do is, well, here we would just sort of draw this as going off. And maybe let's sort of draw it like this. And then, of course, we would draw like this, where what we're saying is, well, this 1 and 1, right there, wrapping around to here. So, right, this would actually be a group of 2. And again, hopefully people have learned this, right? So this should just be a recap. Right, so so if we do this then, and of course we want to try and make as big groups as possible, right, for it to be as sort of optimized as possible. So here then, well, there's going to be this group of 4, because of course, well, there's no way to make this bigger. Obviously keeping these kind of rules in mind that we've said. Now, what people might be willing to do is just think, okay, well, there's 2 remaining, right? Just fill in those 2, but that's actually going to be wrong. And the reason that's wrong is because, well, here, of course, we can actually make a group of 4. So just making this, bottom row of 4. Since again, we have to make them as big as possible in order for it to be sort of as simplified, right, or as optimized as possible. Right, then we want to write the Boolean expression from your answer to part right CI as a simplified sum of products. Right, so the way to do that then is, well, we just look at what values change. So I think what I'm going to do, let's start on this 2 by 2 square. Well, of course, right, this one here. So if we look at what values change, well, if we look at A, right, well, A is 1, right, and A is 0. So because it changes, well, we ignore it, okay, because, this doesn't tell us anything about it. Right, then if we look at C, well, again, C also changes because we have a 1, right, we also have a 0. So we also just ignore C. Now, the only constant then is 0, is B, because B is 0 in both times. Now, what that means is, well, of course, because it's 0, right, therefore that's going to be not B. If it was, for example, 1 both times like this, right, well, of course, then it would just be B. Right, again, we're just going to OR them. And, now then, of course, if we look at this bottom row, let's see what changes. Right, in this case, well, 1 is constant, okay, so this is going to be A. Then if we look at B, well, B, is 0, right, but then here B is 1. Likewise, if we look at C, right, well, here C is 0, right, but here C is 1. So in this case, right, the only thing that's constant is A. And since A is 1, right, of course, well, that's right, that's why we write A, right, rather than not A. For 7, we want to describe what is meant by a digital certificate. So I think for this, we can say what is going to be a digital document that is used to authenticate someone or maybe a device's identity. And right, it's going to do that, well, let's say, right, obviously it's going to contain their public key, and it's also going to contain either some personal or business information, like, for example, their email address. If it's a business, right, maybe it can have the address of their headquarters. It could have, for example, the company telephone number, things like that. Right, so let's just try and write that then. A digital document used to let's say authenticate. We can say someone, maybe let's say someone's, right, slash a device's, let's say a device's identity. I suppose what we could say, like, maybe on the internet or kind of over a network. I think let's say on the internet. Although I suppose, really this doesn't have to be on the internet, it could also be offline, to be honest. Right, and then I think we can just say what, probably, well, let's just say what it would contain. Right, so this will contain, and we can say what the, let's say the persons, or the sort of devices, right, because obviously it might be a server. Let's say the person, I think that's fine. Right, the person's public key. Yeah, let's say, and I mean in brackets we could say, right, used for encryption. I suppose what encryption, yeah, and verifying. Maybe what verifying their digital signature. And then, yeah, I think we can also mention what it's going to have. Of course, okay, right, so it's going to contain the person's public key. Let's say maybe, right, some identifying information. Yeah, right. Well, let's say, right, e.g., I don't know, maybe email. Yeah, we could say, let's say, like office location. Right, and I think we can also say it's also going to contain the certificate authorities. Yeah, public. Okay, hang on, no, right, sorry. It's going to contain the digital signature of the certificate authority. Right, yeah, and the right digital signature. And of course, well, the reason it has the digital signature of the certificate authority that signed it is basically, well, just to sort of, well, let's say, you know, sort of verify that the sort of, I guess you say, what, to verify that the digital certificate is valid. Yeah, verify that, you know, it's not sort of like sort of being forged or something. Right, let's just say that. So yeah, and the digital signature, right, of the certificate authority. Yeah, I mean, I don't know, like maybe here you could just say CA, but I'm just going to write the whole thing, right? Certificate authority. Let's say what, that signed it. Yeah, so I think that's okay. Then we want to explain the role of a digital certificate in creating a digital signature. So I think what we can say that what a digital certificate will contain the public key, and since that's mathematically linked to the private key, then of course, well, you know, when you create the digital signature, people can actually verify that, of course, okay, I mean, let's say people can verify that, you know, these files came from you, because, well, obviously only the person with that private key, like, will be able to have their messages sort of verified, right, you know, with the public key in the digital certificate. So yeah, I mean, probably not the best explanation, but I'm going to try and write it. So, right, let's say, yeah, the digital certificate, right, digital certificate, right, contains a public key, or yeah, okay, I mean, let's say what, generated, maybe generated public key. Right, let's say what, that is mathematically linked, or yeah, sort of mathematically related. Yeah, okay, let's say, yeah, mathematically linked, right, to, yeah, I mean, what, to the private key. And we can say, well, maybe hence, right, so hence, yeah, documents, or, you know, data. Yeah, I know, I mean, let's say data. Right, so let's say data signed, right, with this private key. And we can say what can only be verified with the corresponding public key. Right, verified, yeah, by the corresponding public key. And we can say what, like, hence proving their identity, or yeah, therefore. Right, therefore. Okay, let's say what, proving the origin of the of the data. Yeah, okay, or maybe, yeah, proving the identity, right, of the sender of the data. Yeah, so I think that's okay for this one. Right, then a declarative programming language is used to represent features that are available and the features that are unavailable of on different body styles of a car. Right, so our feature, okay, well, sunroof, right, tailgate, yeah, etc. Right, then we've got body style. Again, that's going to take, let's say, what, one, yeah, because, well, yeah, one, like, parameter. Right, then available, right, unavailable. Right, it says, well, these clauses have the meanings. Right, so, well, 1 means, yes, sunroof is a feature, right, 10, saloon is a body style, Yeah, okay, right, 15, sunroof is available on a hatchback. Yes, of course, here we see, well, this is the feature, this is the type of car. And then likewise, right, 20, hang on. Right, 20, well, sunroof is unavailable on a convertible, because, yeah, I guess here. Right, then says sliding doors is a feature that is available on a minivan, but unavailable on a hatchback. Write additional clauses to represent this information. So first then, well, let's look, is sliding doors an actual feature? So here what we've got, sunroof, yeah, tailgate seats. Yeah, so I think here then there's actually no sliding doors. So let's just write this additional fact. Right, that's going to be feature. And then let's say, yeah, sliding doors. And I think what they're using underscores just to separate the words. And then here, let's remember, just have the full stop at the end. Right, then we say what is available on a minivan. So let's go available. And if we actually look at the format here, right, they say what is going to be the feature, then it's going to be the car type. And then unavailable, well, it's going to be the feature again, right, then it's the car type. So, right, it's going to be available, yeah, okay, I mean, this is quite long to actually write this, sliding doors. And then, right, that's going to be minivan. Now, I would say here, probably do check. So, yeah, okay, minivan, right, spelled like this. And then if we see hatchback, of course, right, spelled like this. Right, so of course, well, this one is then just going to be unavailable. And yeah, again, that's going to be sliding doors. Let's have the underscore. And yeah, hatchback. Okay, right then, using the variable options, the goal, right, available, yeah, options, and then, well, saloon, or, yeah. Right, it's going to return, okay, it's going to return reversing camera. So if we have a look at that, then saloon. Right, if we see, yeah, so I guess here, right, saloon, and yeah, that has this, okay, reversing camera. Right, we want to write the result returned by the goal, options of hatchback. So yeah, what does hatchback have basically? So we see what hatchback has: a sunroof, and it also has, also a reversing camera. Yeah, okay, so just those two. Right, so I think, yeah, I'm probably just going to separate them with a comma. So let's go sunroof, and yeah, let's make that small s. Right, then also what reversing camera. Right then, F may be available for B. Right, so well, F is a feature, I guess. Right, and B is a body style, and F is not unavailable for that body style. Okay, I mean, so I guess this is talking, well, yeah, like possibly this feature is available because I guess there's like a huge number of features, and maybe the person hasn't just got around to like filling them all in. So we're saying, well, if it's not been marked as unavailable, right, therefore it's kind of a possibility that it is available. So yeah, what we can say then, if we want to check, right, F is a feature. So what we want to go feature. So right, hang on then, and yeah, how does this look? This just has, yeah, okay, 1. So right, we go feature F because, well, I mean, this is going to return true or false. So it's saying, right, this feature, right, then I think the comma is used for and, although in the mark scheme they do also allow and. Although, yeah, I think if you actually use Prolog, right, Prolog, they do use the commas. Right, then we want to go what body style. So yeah, it's going to be what feature F exists, right, and body style. Right, that's going to be B. So of course, yeah, checking both of those exist. Right, then we want another and I suppose here we just want to go, right, not. Because, yeah, if we go, for example, like unavailable, what is it going to be? Unavailable, yeah, F, then B, I think. Yeah, because, right, I mean, so body style is the type of car. So, of course, well, if we go unavailable, FB, well, obviously, I mean, that means it's not available. So if we just go not, of course, well, that's just going to invert it, right? So let's go, right, not unavailable. Right, and then that's going to be FB. Now, hopefully this makes sense. Right, I mean, if you haven't actually had, practical experience using Prolog, then, of course, well, I would recommend downloading Prolog. And actually, like, that's probably not accurate to say because I guess Prolog is just kind of the specification, right, the sort of syntax of the language. There's actually different implementations. Now, I mean, the one we use is called SWI Prolog, and I think this is recommended for sort of, schools education. Yeah, even though this one is actually quite old. Yeah, I don't know. Okay, I mean, I don't know. Like, maybe there's a way you can find a more modern one, but I think this is just what we use, right? This is what the book also recommends. Right, then we want to explain what is meant by deep learning in relation to artificial intelligence. So what deep learning? Well, I mean, one's going to be what, let's say, neural nets. There's also going to be, well, let's say HL, right? The hidden layers. We can say what it's going to create. I don't know. Okay, well, let's say a model. So you can say what a neural network model will be created based on large amounts of training data, and that will update the weightings in the hidden layers. And then what's going to happen is, well, when you have let's say unseen data, well, that will be loaded in, and I guess basically what it's going to yeah, well, it's just going to be sort of predicted by the hidden layers, and of course, well, they'll then give an output of like which yeah, I know, I guess like which classification it thinks it is. Yeah, so I think we can say that maybe, let's say what is a machine learning technique. Yeah, okay, right, let's say machine learning technique. Yeah, let's see what that uses. Yeah, or we can say what that generates. Yeah, let's say, right, that generates a neural network model. Okay, right, yeah, neural network model, right, containing many hidden layers, or okay, well, let's say, right, containing input, right, many hidden layers and an output layer. Yeah, so right, an input, right, many hidden layers, yeah, and an output layer. Yeah, and we can probably say what the hidden layers will have weightings. Or yeah, let's say maybe weightings. What will be given to the nodes or edges. Yeah, I mean, I think let's say edges probably. Yeah, okay, I think let's say edges. Right, will be given to the edges. Right, yeah, okay, well, let's say, yeah, for each node. Yeah, okay, right, let's say, yeah, for each node, right, in each hidden layer, or yeah, in every hidden layer. Yeah, and what we can say, what this uses back propagation in order to train. Yeah, so let's say weightings will be given to right, edges for each node in every hidden layer. Yeah, let's say during the training process. Okay, during the the training process. Yeah, let's say what these weightings will be kind of updated. Alright, hang, yeah, okay, right, these weightings will be adjusted, right, due to back propagation. And yeah, okay, I mean, well, this one I'll explain in a minute. Right, due to back propagation. Yeah, and we can say what when, let's say when, kind of like when we're trying to classify something. Yeah, let's say when trying to classify. Or yeah, okay, I know, right, let's say, yeah, when using the finished model, or when using the finished neural network. Right, when using, yeah, the finished neural network, we can say what the input, sort of the input data will be sort of broken down into, various values. Of course, it will then, travel along the hidden layers and arrive at the output layer. So yeah, let's try to sort of say that in a concise way. Maybe, yeah, the input data. Or let's say the input data, yeah, will, I don't know, I mean, let's say travel. I mean, it's probably not the best word, but let's say, yeah, travel through the hidden layers. Yeah, of course, well, that's going to be based on the weighting. Right, hidden layers. Yeah, let's say, well, and arrive at one node, right, in the output layer. Right here, yeah, one node, right, in the output layer. And I think, well, just to explain backpropagation quickly, like what this is going to be, yeah, I think not much space. Let's say, well, I mean, right here, these are just our input layers. Let's say, right, these are just our hidden layers, and I don't know, maybe we've just got a few here. And well, of course, right, these can just be our output layers. Now, if, for example, we have, I don't know, maybe like this one, and then, yeah, this one, right, then this one, and we say, well, this has a value of, say, 0.7, right, this has a value of, I don't know, like 0.4, right, this has a value of, like, 0.2. Now, let's say, for example, if we found that, well, okay, let's say the result that it generated was wrong, then what we would do is, well, I mean, we would go back, right, we would, of course, adjust these values in order to, I mean, kind of just like randomizing them. Yeah, of course, in order to hopefully think that, well, let's say the next iteration is going to be more accurate. And I think it's not really random. I mean, it's actually based on the sort of degree of error. So yeah, based on the degree of error, of course, you can then increase these values or decrease these values. Yeah, to hopefully get more and more accurate each time. Okay, then 10, state a condition that must be true for an array to be searchable for a binary search. So this should hopefully be quite simple. This just means what the array has to be ordered. Yeah, all right. So the array has to be ordered, and of course, I mean, well, this could be either in ascending or descending. Yeah, okay. So I think that's fine. Right then, complete the given pseudocode to find an item in a 1D array names of type string using a binary search. Right. So we've got names. What that's got is that 100,000 elements. Right, the top of list. So I'm not sure why they call it this. I mean, this is basically the start. So yeah, like for me, I'm just going to call that start of list, right? It's kind of more, yeah, sort of more easy in my head. Right, then of course end of list, right? The current item, yeah, well, the item to find. Right, then we've got a Boolean, whether it's found, right? Another Boolean, whether it's not in the list. And of course we're here, right? The start of list and the end of list. Right, well then it says which name do you wish to find, and they input what they want to find. Right, then we see, well, not in list is assigned false. But if we actually look, well, we haven't assigned anything to found. So I think here, well, let's just go found. And of course, we're at the start, right? We're just going to assign that false. Right, then we want to check. So, well, okay, I mean, let's think when we want to keep looping. Of course, well, one is going to be, right, if found equals false. And then I suppose the other one is, well, not in list, right? That's also false. Let's just go through a quick example then. So if we have an array, let's say what 1, maybe 3, right, let's go 4, right, maybe 6, and yeah, let's say 8. Now let's imagine we're trying to find the value 7. Of course, what's going to happen, what the top pointer or the start pointer is going to start at the first element. The end pointer, of course, well, at the end element. Right, then we're going to get the midpoint, right, the middle element. So in this case, well, that's going to be, well, yeah, of course, that's going to be 4. So then what we're going to say, well, is the element we're trying to find, right, so let's say 7, is 7 bigger than 4? And, well, if it is, right, then of course what we do is we're going to move this top pointer up. And we think, well, obviously, I mean, yeah, this is not the, obviously, well, this is not the element, right, that we're trying to find. This is not 7, because, well, we've sort of already checked if it's equal. So what we're going to do then, we're going to move this top pointer up to here. So, yeah, now the top pointer is obviously on this element. Now what we do is, well, now we then find the, well, of course, the sort of middle element of these. But since there's only 2 elements, well, then what we do is, I mean, we're just going to move the top pointer to be the same as the end pointer. Yes, since again, we've sort of checked that, well, obviously 6 is not equal to 7. Now what we can say is, well, if the right, if the top pointer is equal to the end pointer, right, and of course, the element is not there, well, of course, well, that means that obviously, well, yeah, of course, you can say we've searched every element, right, we've not found it, therefore, of course, we would say, right, this not in list would therefore become true at that point. So I think, yeah, if we just think of this and then, well, this is going to be not in list is false. Because, I mean, again, so, when we say not in list is true, well, it's going to become true, when we've searched every element. And of course, yeah, well, at that point, we can of course just quit because, well, obviously, yeah, we know it's not in the list. Right, so current item, right, that's going to be assigned the top of the list plus the end of the list div 2, right, so just finding the midpoint. So, right, we're going to do something and then we set found to true. So I suppose this is obviously checking, right, if the element to find is equal to what we're searching for. So right, the array then is going to be names, and what the index is current item. So yeah, let's go right, names at index current item. Right, and then if that is equal to to find. Right, of course, well then we set found to true. Right, else if the top of list is greater than the end of list. Well, okay, yeah, so right, greater than or equal to. So I think then that's talking about this condition, right, where we've searched every element. So when we've searched every element, well, let's set the not in list to true. Okay, yeah, true. Right, then else, right, if to find is greater than the sort of current element, right, so this is what we said, where we want to, move this top pointer up. So here then, what that's going to be, is it, yeah, top of list? I think that's what they call it. And actually, we can sort of see what they've done here. So yeah, really, you can just sort of use the same format. So it's going to be current item, but then rather than -1, well, it's going to be +1. And of course, again, that's because the reason we said here, I mean, obviously, well, we've checked this for already, right? Therefore, of course, well, yeah, we only need to sort of, like check these two. Likewise, if it's smaller than 4, well, of course, again, we know it's smaller than 4, so it's not this one, right? Therefore, we would move the end pointer right down to this one in that case. And of course, yeah, the top pointer is going to stay here. That's why it's going to be, well, obviously, yeah, moving it down -1 from the current index, or yeah, moving it up, right, +1 from the current index. And then, yeah, okay, right, so that's all of them. Now, I mean, obviously, there is a little bit of a tip, and I suppose let's go, yeah, hang on, right, not in list equals false. There is a bit of a tip that, of course, well, since here we say not in list, you'd also want to look through here, and like if there's nowhere where we update not in list, well, then of course you can think, well, that's going to be invalid, since there's obviously a reason why we're actually including this in this and, right? I mean, yeah, obviously, like at some point this can possibly change. Yeah, that's why you're going to want to have something that changes not in list here, because I think that's going to be a common mistake a lot of people might make, right? Maybe they wouldn't update that one. Right, anyway, next we want to describe the performance of a binary search in relation to the number of data items in the array being searched. Right, refer to big O notation in your answer. So binary search, well, that's going to be a log n algorithm. So what that means is that as the number of items increases linearly, the time taken to search increases logarithmically. And honestly, I think most people probably have sort of much better maths than me. But I mean, well, just to recap, logarithmically is something like this, where, like, I don't know, maybe let's say here this can be, let's say, like 1 million. Or let's say like 1 million. This one is, let's say, I don't know, like 1 billion. I suppose, well, let's do maybe M, right? This can be sort of giga, right, for billion. And of course, yeah, I don't know, like, let's say this here, right? This can be, what, trillion? So yeah, 1, like, tera. And I think, I mean, if you actually do this, if you do sort of, log, right, let's say log base 2 of 1 million, I think that's approximately 24. Whereas if you do, say, log base 2 of 1 trillion, I don't know, like, is that going to be like 48 or 40 or something? So what you can say, and again, like, maybe my calculations are completely wrong, but what you can say is that, well, going from 1 million to 1 trillion, well, that's like 1 million times more in terms of the number of elements, right? But like, even by increasing the number of elements, right, 1 million times, actually the number of comparisons we have to do has only actually, well, I guess, doubled, right? It's increased by 2. So of course, yeah, that's why, logarithmic algorithms are going to be good, because like, even if you have like huge data sets, well, of course, right, since it's, logarithmic growth, right, it's actually not going to get that much slower. So yeah, let's try and mention that. So we say, well, as the number of data items increases linearly, the number of data items increases linearly. Yeah, we say what the, let's say the time taken. Right, the time taken, yeah, let's say only increases logarithmically. And I think, I mean, let's also give the actual, sort of, I guess, what O log n. So let's say, right, yeah, binary search. Yeah, so just to be sort of specific, right, binary search is, is a, or maybe an, let's go by O log n algorithm. Yeah, so I think that should be okay. Right then, is this the last one? Yeah, okay. Right, so reduced instruction set computers, or RISC, and complex instruction set, or well, CISC, right, are two types of processors. State two features of RISC processors. So RISC, what we can say, there's a relatively small number of instructions. Yeah, okay, relatively small. Let's say yes, small and simple set of instructions. Yeah, so I think that's fine. Well, I don't know, let's see what the processor supports. And then I think for other ones, I mean, you can talk about pipelining, right? So it's going to be relatively easy to pipeline. You can sort of, there's a relatively few number of addressing modes. You can also say the instructions should execute. I mean, most of them will execute just in one clock cycle. You can also talk about, if you're talking about the control unit, well then that's going to be, that's going to be sort of what I guess hardwired, right, rather than sort of using the firmware, right, which is what CISC would do. But I think, let's probably talk about pipelining, right? That's one of the main things. So let's see, pipelining is relatively easy to do. Let's say relatively easy. And I suppose we can say since most instructions can be complete in one clock cycle. Or, okay, well, let's say most instructions can execute in one clock cycle. Can execute in one clock cycle. Because, of course, if you talk about the whole thing, right, there's 5 stages. First the instruction fetch, then the instruction decode, then the operand fetch, the instruction execute, and finally the write back. So of course, if you assume that each of those stages is going to take one cycle, therefore the whole the whole instruction is going to take 5 cycles. But of course, because they're pipelined, then I mean you can think of it that obviously just the execution stage is only going to take one cycle. Let's say since most instructions can execute in one cycle, then we want to outline the process of interrupt handling as it could be applied to RISC or CISC processors. So I think interrupt handling, I mean, what you could mention that first is going to check sort of the priority of the interrupt, and if the interrupt has a high enough priority, well then it's going to be handled. I mean, then of course you can say, well, the status of the registers, or let's say the contents of the registers, will be saved into memory, or just added to the stack. Then of course the let's see what the address, or the start address of the ISR, the interrupt service routine, is going to be loaded into the program counter, where of course then it can just be fetched, decoded, executed. So that of course that means the ISR is then going to fully execute. When the ISR is finished executing, I suppose if you want to be detailed, what you say, then the process will check, has there been any more interrupts? Again, check that priority. Of course, once it's handled all of the interrupts, once there's no more, then it can then load back the original program, or I suppose let's say load back the registers from the original process back into memory, and then of course that can then continue executing, because of course again let's say the the PC, the MAR, the MDR, CIR, obviously they've been restored with their original contents, from what let's say from when the process was interrupted. So I think and obviously I mean we don't I mean this is not a 6 marker, so we don't need huge amounts of detail. Let's just say maybe when an interrupt occurs. Well, let's say the priority is checked, or let's say the priority is checked. Well, let's say if high enough, what we say the contents of the registers of the current process will be saved to the stack, or pushed onto the stack. Let's say that the contents Yeah, okay, I mean, or hang on, let's say, yeah, register contents, because otherwise we need to say like of. Right, so yeah, register contents. Right, yeah, of the current process. Right, let's say, yeah, are pushed onto the stack. So if we think, well, the stack, I mean, this is just RAM. Right, pushed onto the stack. Let's say, right, and the, let's say, start address. Okay, right, start address, yeah, of the, well, let's say interrupt service routine. Yeah, okay, not Y, right, interrupt service routine. Let's put in brackets ISR, right, is loaded. Yeah, let's say, right, loaded into the PC. I suppose here, right, let's say program counter. Right, PC, let's say, yeah, and the ISR executes. I mean, let's see what, like, fetch decode executes. Of course, it's going to complete that. Right, and then, yeah, okay, so let's go, right, when finished. Right, when finished. Right, let's say what the original, let's say the original register values from the process can be, reloaded back into the registers. Yeah, let's see, right, the original, okay, the original register values, right, can be reloaded. And the original process can continue executing. Okay, right, original, yeah, process, right, can continue executing. Yeah, okay. Right, then the last one, explain how pipelining affects interrupt handling for RISC processors. Alright, so this one is a bit tricky. Do I have... Yeah, okay, I've got space here. So let's say what we had the 5 stages, and hopefully I can remember these correctly. So the first one was going to be instruction fetch. Right, then we got instruction decode. Right, then we got what, operand fetch. Right, then we've got what, instruction execute. And then finally, well, write back. So that's just, obviously, well, writing the result to memory. So let's say we've got, I don't know, like maybe this instruction we've got an add. Let's say, yeah, maybe in the decode we've got, I don't know, some like, LDD. And of course, I don't know, like maybe say like add 5. Let's say this can be, yeah, like let's say load what, direct addressing 7. And of course, like these are going to be different stages. So, yeah, hang on, I mean, maybe let me just redo this. Like I'm probably just going to simplify it. Right, maybe we've got one thing just at stage 1 of the fetch. We've got another instruction here, obviously stage 2. Yeah, another one here at stage 3. Right, another one here, stage 4. And then obviously, yeah, this one, right, is obviously nearly finished. So what we can say is that, let's say, I don't know, maybe there could be an error here, right, in this, execute stage. Now, what's going to happen? Well, of course, since this write back is finished, well, I mean, yeah, obviously, this can be written back. But then, like, all of these, so the ones at the previous stage, right, the instruction fetch, right, decode, yeah, operand fetch, all of these, well, yeah, these instructions just have to be discarded, right? So they would be discarded from the current pipeline. And then what you would say is, of course, well, yeah, of course, well, this write back can finish, but everything at the previous stages have to be discarded. And then obviously, well, when the ISR has finished executing, right, well, I mean, yeah, then what you'd want to do, you just want to restart all of these. So, let's say this instruction is being executed, well, you would want to restart this, but I guess, yeah, restart it from, the instruction fetch stage. Likewise, of course, yeah, this OF, of course, you'd also want to, restart this from the, yeah, fetch stage, right, same as this, right, same as this. Yeah, so hopefully that makes sense. So what we can say, yeah, let's say maybe, what, when, I mean, I guess we can say what, pipelining will increase complexity. Yeah, like maybe we can say that, right? Pipelining. Okay, right, pipelining increases complexity. Right, of, let's say, interrupt handling. Right, and let's say since, I suppose what we can say, like since the, yeah, okay, let's say the instructions sort of in lower stages, or yeah, previous stages. Right, the instructions, yeah, in, okay, I don't know, I mean, let's say lower, I think that's fine, right, lower stages, or yeah, maybe earlier, right, let's say, yeah, earlier stages, right, of the, well, fetch, decode, execute cycle. Right, fetch, decode, execute cycle, let's say what will have to be discarded. Yeah, have to be discarded. Yeah, and we can say what, and the ISR will have to, you know, sort of execute. Yeah, or let's say, yeah, the ISR, yeah, will have to, you know, handle the interrupts. We can say what, yeah, let's say when finished. And I guess we say, right, when finished, the discarded instructions will then have to restart, right, from the instruction fetch stage. Right, when finished, yeah, okay, or let's say that, right, the discarded instructions, right, yeah, discarded instructions will have to restart. Okay, yeah, restart from the instruction fetch stage. And of course, right, that's going to be stage 1. Alright, so again, guys, I mean, hopefully this video is useful. Probably that's gone on super long. Yeah, I'm not sure. But again, of course, any any questions, just ask in the comments. And if the video is useful, well, then see you again in the next one.